All right, we're diving straight into the wizarding world today. But we're not just here for the cool spells. Nope, we're here to pull back the curtain and uncover the secret physics that actually makes all that magic work.
I mean, just picture it, right? You're soaring high above the Quidditch pitch, the wind is just whipping past you, you can hear the roar of the crowd, a bludger comes rocketing past your head, and way off in the distance, you catch that little glint of the Golden Snitch. It feels like pure, totally untamed magic.
But what if I told you that every single swerve of a broomstick, every flick of a wand, even the crazy flight of that snitch, it's all governed by a hidden set of rules? Like a kind of magical physics that, once you get it, gives you this master-level insight into how the whole thing actually works.
And this entire magical system? Well, it really just comes down to one fundamental concept, something straight out of O-level physics, actually, forces. So yeah, let's start with the basics.
Okay, so in the world of physics, a force is super simple. It's just a push or a pull that one object exerts on another. That's it. It's the reason anything moves or stops or changes at all.
And guess what? In the wizarding world, they just have a different name for applying a force from a distance. Yep, they call them spells. So when you cast Wingardium Leviosa, you're not just saying some fancy words. You're literally applying an upward pull, a force, on that feather.
So any force, doesn't matter if it's magical or not, can do one of three things. First, it can change an object's speed. Think of a beater just smashing a bludger and sending it rocketing across the pitch. Second, it can change an object's direction, kind of like how a Protego charm deflects a jinx. And third, it can change an object's shape. Like, when an unlucky wizard accidentally squashes their potion ingredients.
All right, so let's take a look at some of these everyday spells or, forces that are constantly at work, even inside a magical castle like Hogwarts.
First up, you've got friction and air resistance. These guys are the forces that are always trying to oppose motion. When you're flying your Nimbus 2000 and you feel the wind pushing against your face? Well, that's air resistance. It's just the force of all those tiny air particles hitting you, trying to slow you down.
And honestly, you'll find other forces hiding in plain sight all over the place. Take tension. That's the pulling force in a rope or a chain, like the ones holding up those massive chandeliers in the Great Hall. Then there's the normal contact force. That's just the pushback you get from a surface. It's the only reason your potions textbook doesn't fall right through the desk. And upthrust? Well, that's the upward push from water that keeps things afloat, like those little boats that carry the first years across the lake.
Okay, but what happens when these forces clash? Because in physics, just like in a wizarding duel, forces can work together or against each other. And the cool part is we can actually calculate the winner.
See, when forces are balanced, they just cancel each other out perfectly. The book's weight is pulling it down, but the table's normal force is pushing up with the exact same strength. The result? The total force, we call it the resultant force, is 0. And so, the book doesn't move. It's like it's in perfect magical stasis.
But when forces are unbalanced, that's when things get interesting. So here, you've got one person pulling with 100 newtons of force, that's just the unit we use to measure force, and the other is pulling with only 80. They don't cancel out, right? There's a leftover or a resultant force, and the rope is going to accelerate in the direction of that stronger pull.
And we can apply this exact same logic to a wizarding duel. Seriously, imagine one wizard spell is pushing with a force of 100 newtons and the other's is pushing back with 80. The winner is decided by the resultant force. You just do the math. 100 minus 80 gives you a 20 newton advantage for the stronger spell. That beam of light, it's going to surge forward and win the duel. Simple as that.
So all of these interactions, from tiny floating feathers to these epic duels, they're all governed by three huge, profound principles. And they were discovered by a muggle, believe it or not, Isaac Newton. The best way to think of them is like the master spellbook for how literally everything moves.
Okay, so there's three of them. First, you've got the law of inertia. That one explains why things either stay put or just keep moving. Then there's the law of acceleration, which is the secret to how you actually change that motion. And finally, the law of action and reaction, which tells us that forces always come in pairs. And these three laws together, they pretty much explain all the motion in the entire universe.
So that first law is all about something called inertia. Basically, an object that's not moving, it's going to stay not moving. Just think of the Golden Snitch, right? It's hovering perfectly still in the air before the match starts. It's not going to move an inch until some kind of force, like the push from the air after the whistle, gets it going.
All right, Newton's second law. This one gives us probably the most famous equation in all of physics. Force equals mass
times acceleration. You've probably seen it, F equals ma. This little formula is the key, the absolute secret that connects how much force you use, how heavy something is, and how quickly it's going to speed up.
So what this law tells us is pretty intuitive, actually. If you use the same amount of force, a heavier object is going to accelerate a lot less. I mean, it's way easier to get an empty shopping cart moving than one that's totally full, right? And in the wizarding world, this means it's going to take a way more powerful spell to move a giant mountain troll than it does to just levitate a tiny little pixie. Mass absolutely matters.
And finally, we have the third law. For every single action, there is an equal and opposite reaction. Ever wondered why when a wizard casts a really powerful spell, they might feel a kickback from their wand? That's Newton's third law in action. Your wand pushes the spell out, and the spell pushes right back on your wand with the exact same amount of force. It's a two-way street.
Okay, let's put all this stuff together now and break down one of the most insane magical objects there is, the Golden Snitch. I mean, how does it pull off those incredible physics-defying moves? Well, here's the secret. It doesn't.
Here's the thing you have to get. The snitch might be flying at a constant speed, but its velocity is constantly changing. And velocity is just speed in a specific direction. So every time it turns, its direction changes, which means its velocity changes. And in physics, any change in velocity is, by definition, acceleration. So get this, an object moving in a circle is always accelerating, even if its speedometer stays the same.
And what does Newton's second law tell us? If something is accelerating, there has to be a force causing it. For anything moving in a circle, we call this the centripetal force. It's a force that is always pulling the object towards the center of the circle. So it's that constant inward pull, generated by the snitch's tiny little wings, that keeps it turning, instead of just flying off in a straight line, which is exactly what Newton's first law says it wants to do.
Now, how much of this centripetal force you need depends on three things: the object's mass, how fast it's going, and how tight the turn is. That's the radius. So, to make the snitch fly faster, or to make a really tight turn with a smaller radius, its wings have to generate a much greater inward force. And that right there is why its movement seems so impossibly quick and agile.
So, now that you get the rules of motion, let me leave you with a question. We know from F equals m that acceleration is just force divided by mass. So if you're a Quidditch seeker and you are desperate to catch that snitch, what's the better strategy? Should you choose the lightest possible broom to minimize your mass? Or should you go for the broom with the most powerful thrust to maximize the force? Think about it. The answer is right there in the physics.